have talks basically spanning everything in the physical sciences that I could find with Josh and Dick that require real-time interaction. Things like fusion plasmas, high-energy physics, light source experiments, a lot on astrophysics today and at the end of the week, and then we also have people talking about weather analysis, both severe storms like tornadoes and then tsunamis as well. It's a very interesting mixed audience, and so I know certainly from the astronomy side, when I've given talks here before, I try to focus it so that our mathematicians and computer scientists can understand it. I expect a lot of questions, and especially in the interaction and the break time. Josh and I will be organizing a couple of panel discussions and drinks at some point during the week after the workshop session ends. So we look forward to a fun and exciting week. Our first speaker, we've had there was a lot of juggling this weekend due to flu hitting some of the speakers here hard. And so our first speaker has filled in for Mario York, who was originally on the schedule. This is Eric Bellm, who I have known before he made his trek up to Washington recently when he was at Caltech and setting up ZTF. He's here to tell us today about alert streams in the LSST era, and it's a wonderful talk to start off this workshop because several of the programs will be addressing the Large Synoptic Survey Telescope and the challenges that we will face and the great science that we can be rewarded with in just a few years. So Eric, by all means, take it over. Thanks.
All right. Thank you, Peter. And thank you to Peter and Josh again for the opportunity to speak and to fill in for Mario, who obviously sends his regrets that he couldn't join you. He just got felled by illness sort of at the last moment. But it gives me the lucky privilege to fill in, and I'm sorry not to be able to join you in person for what looks like a very interesting program. So I'm starting with Mario's title here, which is Alert Streams in the LSST Era, Challenges and Opportunities, and taking some of his ideas and definitely giving them my own spin. So my role, I'm a faculty member at the University of Washington, where I'm the Alert Production Science Lead for LSST Data Management. That's a handful, so let me break it down a little bit so you know where I'm coming from. LSST is a new telescope that's being built. I'll have much more to say about it later in the talk, but you can see a rendering here. This is a very large, sort of billion-dollar scale facility now in construction in Chile that's expected to begin full operations in sort of the 2022 timeframe. And one of the major products of LSST is an alert stream of things that are changing in the sky. And so the question of what to do with that real-time stream and how to make use of it scientifically obviously requires a great deal of real-time decision-making. And so I think it's a great topic for this meeting. So my role, I lead a team of research scientists, developers, engineers. We're building these real-time pipelines, and my job is to make sure that the product we deliver in just a few very short years is going to enable the widest variety of science possible. Along the way, I'll discuss a little bit the broader scientific background. I think it's a little bit of a lead-in to some of the other talks you see on the schedule later today from Josh and Alessandra and Mansi, who will be speaking on similar themes, and I'll give a little bit of a preview of things I think they'll go into much more depth on. So the context here, let me turn to the next slide. The context here with LSST, but also with many other surveys, is these are wide field optical surveys of the sky. So they're running and taking images with CCD cameras in the same sort of bands that we can see with our eyes. And as the night passes, you can see an animation, a simulation of a certain observing strategy. The camera takes pictures, the telescope takes pictures across the sky, and one of several bands and then revisits them. And so over time, you sort of build up this stack of images of specific regions of the sky at different times, at different wavelengths or frequencies. And we can use those to learn about the astrophysical objects that are there. So the scientific goals here are to find things that are changing. And so I'm showing here in the background an image of a very young supernova. You can see overlaid on its host galaxy sort of appearing and dimming. This was a particularly exciting young supernova, one of the youngest ever discovered. And the typical technique that's used is known as image subtraction. You can see the triplet of images in the upper left of the screen. You take this new image and then subtract from a sort of a stack of previous images that tell us something about the static sky that was there previously, and that removes the effect or the presence of things like the diffuse host galaxy. And in the best case, you see popping out there a nice clear point source-like astrophysical transient. And then we can detect those in that difference image and then decide what action to take. And so in particular, for these sorts of transient events that appear and disappear in time, the need for real-time follow-up is a huge motivator because we want to capture as much physical information as we can about these sources before they fade away. And so that can span a huge range of facilities around the world and in space. I'm showing here, of course, the Keck observatories, which are some of the world's premier large aperture facilities for follow-up, able to get very detailed spectra and other sort of measurements of transients. And the upper right is the Swift Observatory, which is a space-based facility that obtains X-ray, gamma ray, optical, UV images, and is very adept at slewing quickly to new events. Of course, the VLA for radio, and there are also robotic facilities like the Las Cumbres Observatory, which has small telescopes that are fully robotic, scheduled around the world, and can be slewed rapidly to follow up rare and interesting events. And already today, the state of the art, as seen in the timeline on the left, is to sort of follow up these events on timescales of just a few hours. So this is a timeline, again, for a young supernova that was discovered within a pair of images taken about an hour apart. And once those data were processed by pipelines that Peter built, actually, then you see triggering, mainly manually at this point, a variety of follow-up resources, including those shown here on this page. So again, the question is, how do you go from those images, those raw images, into the decisions that lead you to allocate your scarce and limited follow-up time on these resources that are highly competitive? Many other astronomers are wanting to use these facilities. And so the bar to be able to interrupt the existing programs and have them slew to your targets is typically pretty high. So you need a good, strong science case and exciting science. And thankfully, we have that in the time domain. One thing to watch out for along the way is that this process is prone to bugs and gremlins and junk and false positives. So on the left, you can see a grid of sort of bad subtractions. The image subtraction process is not always flawless. You don't always get that clear point source that says this is an astrophysical transient. Sometimes you get pipeline failures or weird camera things or optics glints and ghosts. And so one of the challenges that I think is generally solved, but we can always do better, is masking these out. And I think Josh may talk some about some of the machine learning techniques that he was really one of the pioneers of in sort of tagging these sorts of objects as bogus and just letting the real astrophysical transients come through. But as the sort of pile of needles in the bottom corner suggests, even once you've got rid of all the junk, there's still a lot of real astrophysics there as well that we have to sort of watch out for. You're looking for a needle in a pile of needles, in other words. And so finding the event that you care about in the midst of all kinds of other real astrophysics is also challenging. So So I told you about supernovae that are, one of the obvious target cases, but there are other kinds of exotic explosions that come through in these sky surveys, things like relativistic explosions like gamma ray bursts where massive stars drive out these ultra-relativistic jets. In recent years, there's been a lot of excitement around tidal disruption events, where a supermassive black hole at the center of a galaxy tears apart a star as it falls in close to the event horizon. That also creates a unique optical signature. And then there are very energetic explosions, superluminous supernovae, which we're learning more about year by year. And last year, of course, there was huge excitement around the discovery by the LIGO and Virgo interferometers of the first binary neutron star merger. And so there was a characteristic sort of chirp as those two compact objects spiraled together. A flash of gamma rays seen by the Fermi Gamma Ray Telescope in orbit, and then a huge worldwide effort to identify and localize a counterpart at longer wavelengths, the optical and radio. And so that was successful. A number of surveys have been discovered using galaxy catalogs, the source of that emission, and it's already telling us a lot of interesting things about what happens when you take two neutron stars and slam them together. Of course, there are lots of objects in our solar system. They change brightness, but they also move, unlike astrophysical objects further out. There was a lot of excitement this last, actually just a few months ago, the first sort of interstellar asteroid that sort of on a parabolic orbit from outside our solar system. It has this very unusual long cigar-shaped appearance. And so identifying weird moving objects like this that don't have orbits similar to those we expect is very interesting, as well as the ongoing desire to identify asteroids with orbits that would intersect the Earth and could possibly lead to impacts with the Earth that could cause property damage or even larger scale extinction events. And finally, there are all manner of variable stars that appear in these optical images all the time, but are varying up and down. I put a sort of an amusing example here discovered by the Kepler Space Telescope, where you have a time series of the flux of this object, very well sampled because this is a space telescope. And you can see these sort of weird and unusual dips. It's most likely these are due to dust, but their strange shape led to sort of fanciful ideas about alien megastructures that might be occulting the flux of the star. I don't think that's true, but it is certainly an example of looking for strange and unusual things in these large sky surveys. So just to be clear, I'm going to talk about LSST today, which is sort of the future of this field, but it's already a very rich field with many surveys active, and I won't go through this huge laundry list of acronyms, but just to sort of emphasize that there's been, in the last decades, a growing number of these surveys driven by the advent of sort of affordable large format CCD detectors, sort of exploring a wide range of niches and interesting areas of scientific phase space, trying to pursue a range of scientific topics. And LSST is in some ways really the most powerful of all of these, and so for that reason it's particularly interesting as we think about how to make real-time decisions. So today, these surveys sort of use a variety of techniques to identify and disseminate the targets they identify, starting at the most basic level from sort of private databases and scripts that are shared by small collaborations. And then maybe some events are posted on public web pages or sent on sort of manually composed circulars through email or the facilities like the Astronomer's Telegram. And then there are sort of more programmatic interfaces that sort of take input into databases or share things through a network like the Transient Name Server or the VO Event Network. I won't describe these in detail, but just to sort of emphasize that there's a little bit of a continuum here between sort of a manual, science-specific sort of approach to handling targets towards more automated, general-purpose approaches. But even, I think, in the most automated examples that exist today, there still tends to be a specialization of these surveys to the specific science that they're best at. And so one of the ways that LSST differs is that it's really trying to be all things to all people. So LSST is in development, and one of the major selling points and the most relevant for this particular conference is that it's going to produce an alert stream that is of much greater scale in terms of number and volume, but also of sort of scientific generality than the surveys that exist today. So it's really trying to not foreclose on any science case, but to enable as many investigations as possible. So the image here shows obviously a rendering of the telescope enclosure once it's completed its development, and some of the key parameters you see here. It's an 8.4 meter telescope. That's quite large. You know, the largest telescopes that exist today have sort of 10 meter scale diameter mirrors. So this is a large facility. It's going to conduct a 10-year survey, a decade, imaging the southern sky every 3 days and produce about 10 million alerts per night, which is a very large number. And so it's going to take these time series photometry of about 40 billion objects and put them into a database for later study. And so you'll see a little bit of the development progress. We expect first light sort of late 2020 and then transition to operations in 2022. So this is located down on a mountaintop in Chile near some other telescope assets. And so it's really looking at the southern sky. You can see the initial demolition to level the mountaintop site when construction began. So this is what the mountaintop looked like at the beginning of construction, and this is what it looked like a couple weeks ago. So you can see the facility is already largely enclosed, and I didn't have a better image, but I have seen that they are now building the dome support piers. So by the end of the year, the dome should be fully enclosed as well, and the telescope will be starting to move in. So many of us in astronomy have been hearing about and seeing that rendering of LSST for a decade or more now, but we're getting close to the point where it's actually a real survey, and that's very exciting. So LSST is a telescope, of course, with a large CCD camera, but fundamentally its scientific product is a database. All of that data, the images and the catalogs, becomes available to data rights holders in the United States and Chile, as well as various international contributors. The alerts themselves from the alert stream, which I'll describe in more detail, are immediately world public with no proprietary period. And so that's one of the more exciting products available. And there's no science being done by those of us who are building the telescope and the data system. It's all going to be done by the international scientific community. The data flow, LSST again is down in Chile. We're going to send the images up over fiber links, and they will be processed at the LSST data facility at NCSA, University of Illinois, which will also host a data access center for the US and Chile and international collaborators to come and work with the data. There's also a satellite processing center in France, and then the LSST project is headquartered in Tucson. There are also satellite institutions like the University of Washington contributing to the construction of the project. So there are sort of three main processing modes for LSST data. I'll talk today most about the prompt channel, which is this alert stream of 10 million alerts per night that we take, and we process those images in 60 seconds. After the shutter closes, we send those alerts out to the world for decision making and follow-up. That also includes the real-time processing of moving objects in conjunction with the Minor Planet Center to tell us more about the population of solar system objects. So again, the headline number here is 10 million alerts per night. Those require filtering in order to make sense of. So LSST hosts a very basic filtering service. It will take individual alert packets and say yes or no, I want these or I don't. But we'll also send them on to community event brokers that will do more sophisticated analysis and classification I'll talk a little bit more about the role of those community brokers later in the talk. And the alerts are rich, and so they have appropriate IDs for reaching back into the database, as well as a variety of time series information and cutout images like you saw from in that initial few slides. And the idea here is that while it doesn't have the entirety of the information that LSST has about the object, it has enough that it can be a standalone piece of set of information to enable that real-time analysis. So the timeline, how this works computationally, we take two images of one field back to back to allow us to reject cosmic rays and other artifacts. And so we take that first image, and while it's begun and it's exposing, we start loading in our data processing chain predictions about where the known solar system objects are, as well as loading other templates and catalogs we need. We read it out and transmit it. It gets compressed and uncompressed. And then the second image is happening at the telescope. While when the second image the readout is completed, that starts our 60-second clock, the deadline we have to do all the processing of both images and produce the final alert. So again, we compress and decompress that second image, do the basic image processing on the image itself, associate it with known previous detections. In parallel, there's some quality assurance. We produce those alert packets, and then as this is happening on the computational chain, we've already started the next visit with the telescope. And so that second visit is then going to be processed on a second parallel computer processing chain, and we'll swap back and forth through the night in order to keep up with the data flow. And so it continues. The second data processing mode is a little more leisurely. This is called data release processing. It's generally an annual process where we reproduce from scratch all of the data that's been taken from the beginning of the survey. And the point is to do the best possible measurements on all of these sources. And so we employ different algorithms that are somewhat more complex and really take the time to do it right. So again, those are annual typically, and then the goal is to produce the sort of a uniform processing of extremely well-calibrated images. And again, we're reprocessing everything taken by the survey. So this is tens of billions of objects and trillions of observations over the course of the full survey. And these are very sophisticated measurements that are being performed. We'll do detailed models of moving point sources, as well as parametric models of galaxies, which have more fuzzy, blobby, extended shapes. There'll also be non-parametric estimates of the various properties of the sources, colors, and variability statistics. And so what I want you to take away from this is this idea that this is an enormous catalog with a very rich data space that's really well suited for statistical exploration, and indeed that's really going to be the only way to find things in it. Finally, the LSST project can't think of every possible science investigation that users might want to do with these data, but their scale is so large that we've prioritized what we're calling user-generated processing, where we have computing power available next to the data in the data center. And so users with data rights can log in and access and call the same sort of LSST pipelines that we're using to do the processing, but tweak them or modify them to do processing that we don't necessarily perform ourselves. And so we expect this to be a very powerful way to perform new and interesting analysis that's, again, not delivered by the project itself. It's a 10-year survey in six wide wavelength band passes, and you end up with about 800 visits for each pointing. The main survey takes about sort of 85–90% of the observing time. Surveys that broad sort of middle region. You can see about 18,000 square degrees of the sky. And then there's some special programs that do sort of science-driven cadences that are a little different than are conducted by the main survey. So very briefly, I won't go into detail here because this is a general audience. I want to describe sort of the software pipelines and processing pipelines that produce the alert stream. This is the software that our team is building here at UW. And so there's sort of a big flow chart here showing how you take those images from the telescope and then produce alerts out the other side. And so we begin sort of processing the single frames, removing the signatures of the instrument from the CCD images. We do that image differencing process to generate alerts, to find things that have changed, and then we distribute those more broadly to the world. So that single frame processing, take out CCD artifacts, we measure the PSF in the background, and then calibrate so we know exactly how bright the sources are, exactly where they are located on the sky, generate lots of catalogs as well as a fair amount of metadata. The image differencing process then takes stored templates that record our previous observations of a field of the sky and subtract them from the new image. And then we take all the images, all the sources that appear at sort of a 5 sigma threshold in that difference, and we call those difference image analysis sources, DS sources, and associate those both with past detections on the difference image, as well as the objects that are produced by the yearly processing, as well as the solar system catalog. So you have the best chance of knowing whether this little blip that's come up in a new image is something brand new or if it's an object that we know a lot about. And then finally, we take those alerts, we package them together with the cutout postage stamps, as well as a variety of other information, sort of do a little database dump for each source, and put them into serialize them to a file essentially, and queue them out to write them to the world so that downstream third-party community brokers can listen and access each one of these events without needing to reach back necessarily into the LSST databases. So I want to talk a little more generally or philosophically about sort of why I think the LSST alert stream is interesting. Certainly, again, it differs in scale from anything that exists today. It's orders of magnitude larger than the number of alerts that have been seen from existing time domain surveys, but it's also quite different in approach from astronomical databases that exist. So in particular, the fact that it's a streaming interface rather than a batch query to a central database, I think is very interesting. So that means it's very naturally real-time and low latency, and it also tends to be decentralized. So once we send these packets out to many places, the things that happen in the processing in each endpoint sort of don't necessarily have to talk to each other. It's very decentralized. And so that gives sort of investigators the opportunity to do what they want without needing to sort of contend for centralized resources. The other thing that's different than many astronomical surveys to date is that LSST made a policy early on that all of the things that show up in the image subtraction were going to be streamed out as alerts. So I would suggest that, first of all, that suggests the name alert may be a bit of a misnomer, because alert sort of implies to our minds, this is exciting, this is important, this is new. And so over the last decade, there have been lots of sort of astronomers wringing their hands that, oh my gosh, there are 10 million alerts at night, we can't handle that. What can we do with all of these things that are so important? But the fact is, and I think I'm allowed to say this, not all of those things are important. You know, they're just new data points. They're not necessarily urgent. You know, there'll be an alert for a variable star that just bounces up and down at the same period for 10 years, and we'll send an alert on the first day of the survey, and we'll send another alert with its new photometry on the last day of the survey. And so it's not really that these are all urgent events that need attention, but it's more that we sort of turn the database inside out, and we're sending everything out to the community. And the advantage here is that we're not sort of prejudging the science that's interesting. We're not saying that we're only interested in supernovae, and so we're only going to send out things that look like supernovae. And so if it turns out that LSST discovers some really interesting science about, you know, variable stars of some kind, people will be able to write filters and classify them and do that sort of analysis without any permission, without any changes from the LSST project. Again, that's enabled because the packets themselves are very rich. The data in them is world public, and so there's lots of information for classification algorithms to run and to generate the sorts of inference that the data support. So fundamentally, again, the way that users are going to find events they care about and decide to take action is through sort of classification or filtering systems. Now, these may be sort of community brokers, we call them, which are potentially large classification engines that take in the LSST stream and add value to it. But it can also be the simple LSST filtering service that I'll describe shortly. So again, the challenge here is to take this alert stream and winnow it down to the things that we care about, and because it's real time, to focus on the sorts of objects that benefit from that real-time nature, where again, you want to trigger some sort of follow-up and make use of that real-time information. Because if it's not real-time, you might as well wait a year and use the data release data, which will be higher precision and has the benefit of you have all the data in front of you. I've talked about this a little bit, but I just want to talk a little bit more about what information is in that alert packet and why we think that enables all that downstream analysis. Obviously, there's some identification, but there's also the object records for the source that triggered the alert, so that excess in the difference image, as well as the object history of that event going back for 12 months. And so it's also linked into the yearly processing. So if there's some information from the more precise, careful end-to-end processing that will be useful, that will also be available. And then there are image cutouts just for examination, but also potentially for doing the sorts of real bogus analysis that sometimes helps rule out false positives. So it's kind of astounding the number of measurements we're going to cram into these packets, just tons of different flux and shape measurements on the image itself, various kinds of likelihood and probability, and then those light curves and time series statistics, so you don't have to compute yourself whether this object has been periodic in the last year. That will already be there. So it's really kind of a batteries included data packet, and I think will help kickstart a wide variety of analysis. So I want to talk a little bit about the technology and the ecosystem we're examining for sending these alerts out. So in the bottom left corner is that sort of catalog of difference image sources. They get stored in an LSST database and then put into alert packets. And then we queue them up to send them out. And so the full streams go to these community brokers that will do a variety of cataloging and cross-matching and classification. And so some users will want to interface with those directly. And then some will use sort of filters that they upload to the LSST system to select just a subset of events that they care about. And so we're prototyping some technologies that are used in industry to do this sort of handling of this alert stream. I should emphasize that this work is led by Maria Patterson, who's a research scientist here at UW. So we're looking at a number of sort of Apache codes that are open sourced and used widely in the web industry for alert transport, serialization, and also filtering. So I'll walk through these one by one, but the first step, of course, is to move the alert packets around. For that, we're looking at Apache Kafka, which is a distributed, scalable sort of distributed log. We're looking at Apache Avro for serialization. It's a compact binary format that is strongly typed, and so it can be challenging to get your data in because you've got to get the types right, but once the packets are encoded, they're impossible to decode incorrectly. And we like Apache Spark for filtering in particular because it has a nice symmetry between stream analysis and batch processing of archival alerts. So just walking through these one by one, again, Apache Kafka is a distributed log, so each alert comes in and is sort of appended to the log. And the nice thing here is that when someone wants to listen or read this log, Kafka keeps track of where each consumer has what the last alert they've seen. And so it has an advantage over sort of the current VO event transport protocol that you can connect and disconnect and replay the stream as needed without needing to be listen all the time. There's also a little less per event traffic back and forth to be able to stream. So again, this is naturally scaled by adding more computers. It was developed at LinkedIn and is widely used in industry and has connectors in a variety of programming languages. Apache Avro, again, is a fairly structured data format in comparison to, for example, XML or especially things like CSV files. So it enforces a strict data type schema, but allows that to evolve, and so you can throw out fields you don't care about. It plays nicely with Kafka, and we've had pretty good luck with it so far. And then finally, we're looking for that sort of filtering process for the LSST filtering service at Apache Spark, which is sort of a jack-of-all-trades general-purpose cluster computing framework that plays nicely with the Kafka stream, but it also enables connections to databases and other interfaces. So I want to talk now a little bit about the role of these community brokers, which I've alluded to, and emphasize that they play a very important role in enabling decision-making on the LSST alert stream. So the plan is to send the full alert stream to some finite number of these third-party brokers, maybe of order 5, plus or minus several. And they're allowed to do some things that the LSST project isn't or has ruled out. Most notably, they can do cross-matching with catalogs from other waveband and other alert streams. So while the LSST data will provide a lot of information in those rich alert packets, you can learn a lot about astrophysical sources by cross-matching to multi-wavelength sources, radio, X-ray, UV, ultraviolet, and so on, as well as sort of catalogs of astrophysical sources that have been spectroscopically classified, for instance. And so by being able to do that cross-match, it will enable much more secure classification of the events. And that classification process is also something that LSST will not do. So we will never say this alert is a supernova. We'll never say this alert is an RLIRA variable star. We'll give parameters that may make that pretty obvious, but they're just characterization. And so the role of assigning probabilistic classifications in particular is left to the community. So other things that brokers could do, obviously just redistributing those world public event packets to get over some of the bandwidth limitations coming out of the LSST facility. There's a little bit of a fan-out effect that we hope will be produced. They can do filtering. We hope they'll provide some useful user interfaces. And then there's a whole sort of challenge of coordinating community interaction, community follow-up and collaboration that I think there are prototypes and existing sort of features that exist today in the world of how you manage large international collaborations who want to find interesting events together and then pool resources like follow-up telescope time to get the most science out of them. Community brokers obviously can do storage and archiving, and there's all kinds of interesting questions around how you handle annotating the information you learn about these alerts and share it, and then sort of enable citation and discovery. So there's a whole rich range of opportunity here for these community brokers. Should emphasize one of the challenges is they're not funded by the LSST project. There's unfortunately no budget line that they can tap into directly from LSST, even though they're so fundamental to the science. And so managing that process, I think, is one that the US community, and the world community actually, I think, is still grappling with. We expect, again, a finite number of those community brokers to be chosen to receive the full LSST alert stream. And that's largely due to bandwidth limitations to be able to send out those 10 million alerts promptly, but also just to sort of manage the human resources necessary to send that. So we envision a proposal process by which those community brokers will be selected in a couple of years. Again, the LSST project itself will provide a simple mini broker system that's a lot simpler. In particular, the filters that users will be able to upload will only act on single alert packets. They won't be doing sort of cross-matching or some of these more sophisticated operations. And there'll be limitations on the number of alerts they can process for each image, as well as the computing time that follows. But I think it will still prove to be a fairly useful facility for a range of science goals that you can express in just very basic sort of cuts or filters. So here's an example of how you could do a young transient filter with just a set of simple yes/no questions. You send in the full stream. You ask if the point source is consistent with being astrophysical, or if it looks like some kind of image subtraction jump. Then you look at the template image and ask if there's a quiescent counterpart that is stellar. If it is, then you're probably looking at a variable star or maybe a quasar, so you throw those away. Then you demand 2 detections from that light curve that are separated by more than about 30 minutes, and that throws away all of the moving objects potentially from their solar system. And then that gives you a fair number of transients potentially, but then you ask if there was an upper limit last night, and if there was, then you have a much smaller stream of just filtered young transients. That's exciting, because then you could potentially trigger follow-up on those. And so the nice thing about some of the technologies we're exploring is that they're symmetric. You put in a stream, you do the filtering, and you get the stream out the other side. And we think having that same interface on both ends is potentially very powerful. I want to talk briefly about another facility called the Zwicky Transient Facility, which I was involved in at Caltech, and I think you'll hear more about from Mansi later today. This is a new camera that's very different, that provides an opportunity to prototype some of these ideas sort of right now. So this is an image of the large CCD camera that has a very wide field of view. We had first light in October, and the survey is starting basically next week. And we're planning an LSST-like alert stream from this camera that will be, again, public later this year. And we're actually have forked many of the LSST tools, the Kafka and Avro sort of systems, to try to deploy those and understand a little better how they function in practice. So it provides a way to test some of these ideas right away. I should emphasize that these are very different surveys, very different telescopes. ZTF lives on this historic Schmidt Telescope at Palomar Observatory. You can see the pencil-drawn rendering from the 1940s when it was built, but it's nevertheless still a very powerful facility today, even though LSST is state-of-the-art and being fabricated now. So what makes it useful, the number of alerts we expect from ZTF nightly is about 1 million, so it's about a factor of 10 less than LSST. And again, it's going into survey mode now, and so we'll have several years of ZTF alerts to test on before the LSST commissioning and operations periods begin. And so we hope this will be a useful way to seed some of these technologies, some of these ideas about rich alert packets and big alert streams to the community. So I wanted to sort of come to a close by looking again at Mario's title, which was talking about opportunities and challenges of the LSST alert stream. And so in terms of opportunities, I think obviously most notably is LSST is a state-of-the-art, brand new billion-dollar facility. It's extremely powerful. I think the data should be reduced as well as any optical data has ever been reduced. And so I think it provides huge discovery space. There's huge amounts of science that can be done with this data. I think the alert stream idea and these rich data products will enable sort of a wide range of inference. There's no sort of prejudgment of the science that can be done. It's really batteries included. And this alert stream concept, I think, is very interesting because it's naturally distributed. You can bring your own computing, and you can apply your ideas without necessarily any interference or any permission. The challenge, of course, is that that's a lot of data, and the large volumes and large event rates, I think, are going to be a little bit of a strain. And it's not quite as simple as just downloading something to your laptop and running it. And so it's going to require an increase in the computational sophistication of the worldwide community. The LSST cadence, because of the size of the field of view, it's large, but it's not enormous. And so for many sorts of events like supernovae, the sampling that you get from LSST sort of by default is not quite as good as you'd like. And so being able to actually perform inference, decide and classify different event types based on that sparse sampling, I think is an ongoing challenge. There are also faint targets because it's a big telescope, and so we already have limited follow-up resources to be able to obtain that follow-up information that's so necessary to fully exploit any given event. And so that's even more challenging when these events are dim. I think that, again, to make the most of any given alert, you want to be able to join it with catalogs at other wavelengths and other alert streams. That functionality is left to the community brokers that are third parties and not directed by LSST per se. And so it's really a challenge to the community to find a way to fund that effort and make it productive. I think that was an interesting choice by the LSST project to structure things this way. Again, the survey is going to be useful for a wide variety of science goals, but I think the flip side of that is that it's not particularly specialized for any one science goal. And so I think many of us with specific science aims would say, if we could drive the telescope, if we could run the data processing our way, we would do it differently than might be done by sort of the average of all of those. So, and finally, I think there's an open question that people have thought about in the past, but is still a little bit of an open question of how do you share information in this distributed ecosystem where many people are processing and adding value to the alert stream, but aren't necessarily talking to each other. So how do we bring that information back together and share between these nodes of this analysis ecosystem? So to conclude, again, LSST is producing an alert stream of unprecedented scale, great scientific potential. I think it's going to be extremely powerful. And we're using new technologies to deliver that alert stream, testing them now. Should know very soon if we're on the right track. But the big question is whether we will have the community ecosystem necessary to make the real-time decisions to follow these events up and make the most of that potential. I hope that ZTF will provide a useful prototype later this year. So finally, as we think about building these tools, I want to share an idea that Maria Patterson has expressed before, which I think is pretty interesting, which is the language we talk about. We often hear about this alert stream fire hose that is so enormous and so powerful, it's going to blow us away, we're not ready for it. And I think a question we can ask is, maybe we can reframe that and think about what can we build that produces not a fire hose that overwhelms us, but a cute community fountain that allows everyone to play and to enjoy these data. So thank you very much, and I'm happy to take your questions.
Thank you, Eric. Okay, I will relay any questions. I do have several of my own, but I'll start. Anybody in the audience first has a question for Eric. Monsi.
Right. So Eric, there's something you hinted on, but it'd be nice if you could elaborate. Is there any potential in this Kafka system or Avro system to put feedback with new information back into the packets? So say you go and classify an event, can you put that classification back in the packet? And
Did
how
you,
does that then get resent out? Or
I think I did, Peter, but why don't you repeat it for me? I think Mansi was asking if the community can feed back classifications and things to LSST, the project.
Yeah, that's basic. Can it go back into the Kafka stream in some way?
Right. I don't think that is in our plans at the moment. I agree that that's an important question of how to share that classification information. I don't immediately know that the LSST project has a place to put that, because again, we're not in the business of classifying, and so even carrying someone else's classification is not obviously in our purview. And so I wonder, this is a little inside baseball for the astronomers, things like the transient name server, which are aggregating information and classification. I wonder if there has to be an analog like that, or even just that specific service that is acting sort of outside because LSST is big and important, but it won't be the only survey that's operating in the 2020s. And sometimes I think that adding LSST data to that of other surveys will be just as important. So I think maybe that information needs to live outside of LSST proper. But if you think there's a strong advantage to being able to have that inside the fence, as it were, let's talk about it.
What I can say is that at the protocol level, VO event has the notion of kind of a follow-up or annotation on an existing transient. So at least at the protocol level, you can, in a way that maintains provenance, say, I believe that this is this sort of class. And then how you transmit that and who saves it and who rebroadcasts that is sort of at the level that Eric answered. But at least at the protocol level, we have the ability to do it.
Good.
Yeah. I take Josh's point that the existing VO event standard has that ability. I would ask, back to Josh, actually, I don't have a sense of how widely that's used in the community today. I don't have a sense of is that regularly, are people sending spectroscopic classifications through VO event, and if not, why not?
That's, we'll answer that over coffee and beers.
Good.
I think the short answer is it's a critical mass question.
Sure.
That whole project got close to, but I think never really achieved it. And there was sort of
right.
a hope that ZTF and LSST would, by the use of VO event, sort of get a bunch of other communities involved using it.
Excellent.
Hi,
Other questions?
It's Casey Law. I'm just interested in the model of sort of what you've described for the LST is trying to get this data out, and it's effectively sounds to me like a distributed decision-making process, right? You're summarizing data to get it out so that the informed people can make decisions in a distributed fashion. But one of the things about distributed computing, say, is that there are very well-established standards of communication, right? So it kind of touches on this point. But you're developing this, it sounds to me, the LSST is developing this sort of from scratch at quite a grand scale. Do you know of any smaller scale kind of implementations of a distributed decision-making process and like the way the data is communicated that is not quite so big and has been, sort of validated in some way?
That's a good question. I don't immediately have anything that jumps to mind, but I would be happy if there were others in the audience who had pointers. That's a very interesting question, Casey. Thanks.
I had a couple questions here. Of the 10 million candidates per night, what fraction of them do you think will be, bogus?
We have strong requirements on that, which I am trying to remember what strictly they are. I think it's of order 10%.
Okay.
It's extremely. We have extremely rigorous requirements on completeness and purity, and that's a little terrifying to me because it's my job to deliver that from our pipeline.
Okay, that was my next question: is who's working on that? Okay, now I know who to blame.
Yes, exactly.
And then, how are associations done?
Are you thinking
Like,
Excuse me?
yeah, I'm basically, when you find a new candidate and then you want to stream along with it previous detections or non-detections, how do you make that association?
So there are several catalogs we're associating to. You know, the previous, so we have this concept of objects which are coming. They're objects that are they're objects that are coming from the data release processing that are sort of associated holistically. They're detected on the COAD, and then there's this sort of rich modeling process over all the images. For the transients, the objects that are associated from the data release specifically, those will just report the 3 nearest stars and the 3 nearest galaxies. So it's not we're not saying that this is definitely, this difference image source is definitely connected to any of these objects. We're just telling you what the nearby ones are. The question about difference image to difference image is more interesting because that's really what produces the light curve that all the time series analysis depends on. And I would say we're still working on exactly what the algorithm that we'll use there is. They're interesting sort of, there's some interesting work in the literature about sort of doing things like the Hungarian algorithm where you're taking basically all of the objects you have and then all of the new difference image sources and associating them together sort of in one go in order to sort of get the right association. So it's not simply a nearest neighbor process, but we haven't fully implemented or chosen our methodology at this point. We're still testing it.
Okay, because one of the things that I'm wondering about is what you do when you have a supernova going off near the core of a galaxy which is active. And,
right.
And how do you delineate those two? At what level? Do you just throw, I mean, so if you're throwing out catalog data rather than imaging data, this question gets quite interesting.
Right. That's an excellent question. I would say there's an open question of whether so if it's strictly speaking on the core and there's no way for LSST to to resolve that difference spatially, then that will be a single object. There's no way, there's nothing we can do to distinguish it. It would be to the user to decide scientifically that, okay, we have some red noise variation, and all of a sudden here comes something that doesn't look like that anymore. There is the possibility of running sort of a point source specialized deblender on the difference imaging, but it hasn't been clearly made a priority that we'll definitely implement. I think it's an open question.
Okay, I'm just wondering when images, like the quality, say, of the seeing changes from
right.
one image to the next, or from the red to the blue, and
yep.
in one case you say it's on core, and then in the next alert you can clearly see it's off core, and so in any case, something to think about still, I guess.
Yeah, there are lots of really interesting challenges around exactly those questions, and I'd be happy to talk to you about these because, there's an open question of do you reassociate, if suddenly you have a good seeing image and you can break things apart, do you reassociate the past sources or not? Some of that, will come through in the yearly data release processing, but that's not much help in the
not much help in real time, but yeah.
Exactly.
All right, Josh?
This isn't really a real-time application, but we've always thought about the difference imaging and alerts around point sources, so new transients or moving objects in the solar system. I guess Armin Rest and people like him would be interested in finding blobs that are moving, right? So if you're looking for supernovae echoes and dust, those are not point sources. Is there anything within LSST to alert the community to locations of possible things like that?
The short answer is no. There is not anything especially well suited to light echoes that are not point sources. I will say that there are there are some, in addition to the point source model, we'll also fit on difference images, both a trailed source model for streaking sources and a dipole model for, if you have 2 point sources that have shifted a little bit. So those measurements will be included with every alert we detect at the 5 sigma level from point sources. So you could certainly imagine that in some cases, those morphologies might allow you to capture something like light echoes. I wouldn't say that that's the right way to do it, and certainly not the most effective way to do it. And so a situation like that is where you might look to something like user-generated processing, running your own algorithms on the data in whatever manner you thought most effective.
Okay. Fernando?
Probably a very naive question from a non-astronomer, but do these alert IDs, other than their kind of strict time ordering, have any notion of a parent ID? Does the messaging stream have any internal structure so that subsequent alerts are connected to their parents by any chain, or is any such connection about objects or other structure meant to be made by the downstream analysis processes in the community?
Yeah, that's a great question. I think the short answer is the connection is made through the object IDs in the packets themselves rather than anything about the alert stream proper.
Okay.
Sort of another non-astronomical question. Viewing the alert stream as sort of a pending query that's burping out stuff on the underlying database. What do you expect, and that users have access to the underlying database as well as the actual information within the alert? What do you anticipate in terms of generated queries on the underlying data from interesting events or just the average event?
Right, that's an excellent question. So there are, we carry a sizing model for the data access center, which I think has something like of order 100 users executing large queries, which are defined as running for hours or days. I think these models are coming from the experience of the Sloan Digital Sky Survey, which was one of the first that really sort of had a large publicly accessible database. I think it's a little bit of a chicken and the egg problem. If the facility supports it, astronomers will do more queries. If they don't, if it doesn't, then they'll get their information elsewhere. But I think it's difficult to say a priori what the follow-up query load looks like. Certainly the design of the alert stream, for better or for worse, is trying to minimize that reach back. But there definitely will be cases, for hopefully a small subset of events where you really do want absolutely all the information in the LSST database, and think about high profile events like some of the gravitational wave counterparts. You can imagine lots and lots of users trying to get in at the same time to understand LSST's data holdings.
Yeah. Question?
Yeah, so you're trying to offload a lot of the classification to third parties, the community.
Yep.
But at the same time, you have this strong requirement for a real bogus, for completeness and not having many bogus events. Won't that require having a good classifier to do that? And then why don't you expose the results better?
Yeah, that's an excellent question, which is, implicitly, how do we measure our false positive rate without getting some classification? That's a tricky problem, as I suspect Josh will tell you more about. You do need some astrophysical ground truth. Some of that I think we can bootstrap from known sources, known surveys. We also expect to use implanted fakes fairly heavily for this process. But I think that it will be a little bit of a negotiating process through the commissioning period to understand that performance. Maybe the right answer is that there'll probably ultimately have to be some partnership with the community who will check our work. We'll claim a certain level of real bogus performance, and I expect others will take a look at that and see if we're actually achieving what we promised.
Go ahead.
I guess my question follows this up. How are you going to use the community brokers or the information that they produce in order to improve the stream?
That's a great question. A great question. I don't have anything concrete in mind. One thing that is tricky here again is that we haven't yet selected the community brokers, and so we don't even know who sits on the other side of the table. I don't have concrete plans in mind, but I suspect that this is something that feedback from users, feedback from community, as we transition into operations and see where we succeed and where we fail. We'll move from sort of today's requirements-driven construction into more of a dynamic, sort of agile process that community feedback tells us where the science priorities are, where we're falling short, and where we can add more value.
So, Eric, this was the first time I heard anything mentioned about fakes. I guess one question I have is that these are key to determining the rates of any astrophysical transient.
Right.
Has thought gone into how one is going to characterize images in the subtractions on the fakes for purposes of understanding completeness for various, different, I would say, astrophysical phenomena?
Yep. Yeah, great question, Peter. Obviously, I'm very aware of the work you've done here for PTF. We have thought about it a little bit, and we're trying to understand sort of where the boundary lies here on, what's our responsibility and what can we provide that is general purpose and useful within the sort of compute bounds we have. I know that DES and other sort of surveys have done extremely extensive, fakes generation to try to understand efficiencies. I think the scale that they have conducted that is probably out of our scope, just for computational reasons. But I do expect that we want to deliver, and we have discussed at a basic level how we can sort of do the general efficiency, report the general efficiency per image, and make that available. But I think this is something I'd be happy to talk more about with you about how we can make that the most useful.
Yeah, on maybe another tangent to that, is it possible after the fact to put your own fakes in and do your own studies with the data, or at least a subset of the data, as part of the generic processing, or could that be something that we could bring our own computers to and just pull the data and do something like that?
Absolutely, that would be an excellent case for user-generated processing. Again, you'll have access to all of the source code from the pipelines, and again, depending on the scale you're talking about, for those who don't necessarily sit at a computer facility, they could do smaller scale things within the LSST data facility. But yes, it's absolutely possible to pull the data and run our pipelines, and again, we will have fake generating code and of our own, and so whether you just need more numbers of simulations, or you want to do a more careful treatment of host galaxies or something like that, that would certainly be something you could do.
All right, thanks. Any final questions? Okay, thank you very much, Eric.
Absolutely. Thank you for having me.